Hi, my name is Lindsay. I'm working on this year's project with John, Mike, and Jill. And our project's focus is optimizing the path to visit 10 national parks in North America. Today we're going to be talking about the context of our system, give you some background on why we chose this problem, literature review, what our problem statement is, the model formulation algorithms, and then discuss the results and some of the conclusion and recommendations we have going forward. This project will address the optimization of a road trip to visit 10 national parks throughout the United States and Canada. Our goal is to minimize the total distance traveled and therefore minimizing travel cost and maximizing the time spent at each desired destination. This aligns well with the concept of the combinatorial optimization traveling salesman problem, which is a form of mixed integer linear programming, where the traveling salesman visits a number of destinations once while distance and cost are minimized. The motivation behind choosing this problem is trying to alleviate one of the most intimidating parts of traveling, the cost and the time spent planning the trip. Some of the questions we are trying to help answer are, is it easier to stop at point A or B first? Are the distances so far apart that it would be better to fly than drive? All of these variables combine into a fairly complicated problem that can be solved with computational optimization. Next, I'm going to be handing it off to Mike to talk about some of the technologies that exist today that help solve these problems.
Hey everyone, I'm Mike. I'm just going to walk through a quick literature review for our project. Just want to talk about the state of the art and competition for other vendors in our field. So everyone's heard of MapQuest. One of their functions that they advertise is their route planner. They claim that this can optimize your route so that you spend less time driving and more time doing while saving you time and gas money. On top of them, there's also a program called Road Trippers, which claims to help people discover the world around them in an entirely new way by streamlining discovery, planning, booking, and navigation into an engaging and intuitive process. Finally, we have another similar program called Route XL, which claims to help you find the fastest itinerary along multiple stops. So while these programs all accomplish their goal to an extent and meet some type of customer need, we feel that there's an untapped market here for potential growth and business success, and that some of these solutions only account for a small number of variables in optimizing your travel. So moving on to the next slide, I just want to go through our problem statement at a high level. So it's stated as follows. What is the minimum distance that someone can travel to complete their journey between national parks, given 10 destinations across 2 countries? So next I'll pass it off to John to talk about our model formulation and solution algorithm. Thanks.
To solve this problem, we used a standard traveling salesman approach. This traveling salesman algorithm takes just one argument, and that's the distance matrix between each of the parks. In order to create this matrix, we took the lat-long location of every single one of the parks and found the distance to every single one of the other parks using their lat-long locations. This algorithm has 3 constraints in it that are really important. The first one ensures that every single park goes to only one other park. Therefore, you cannot leave Park 1 and end up at both Park 2 and Park 3. The second constraint ensures that you can only arrive at a park from one other park. Therefore, you cannot leave Park 1 and Park 2 and have both of them lead you to Park 3. These 2 combined ensure the most important piece of the algorithm, and that is that every single park is visited once and only once. The last constraint involves the subtour elimination, and this is really important to ensure that every single park is visited in a continuous route. It's possible without this constraint that you have 2 or 3 or X number of subtours in your route where, for example, you visit Park 1, 2, and 3, and then 4, 5, and 6 without connecting Parks 3 and 4. The subtour elimination portion of this algorithm ensures that every single one of these parks has a path to the other parks. These three constraints combined will lead you to the shortest path between all of your parks around. Jill will go over in the next section the results of our specific implementation with the parks that we chose.
As previously discussed, our model is able to take the input of distance, considering this to be the distance as the crow flies between each park in a distance matrix, and then output both the optimal path to take to visit the parks, as well as total distance traveled in degrees given that optimized path. This serves as an optimal park itinerary one should follow, given a set of national parks to visit. In our example case, we are looking at a trip to visit 10 national parks across 2 countries, with those parks represented in the distance matrix on this slide. The program takes that distance matrix input and outputs total distance traveled, shown as the lower bound and upper bounds of around 104 on this slide. You'll also see the optimal path provided at the bottom of the slide, suggesting an optimized trip starting at Acadia National Park in Maine and ending at the Badlands National Park in South Dakota. One of the hardest and most time-consuming parts about planning a trip is figuring out the most cost-effective methods of transportation. Is it cheaper to fly or drive? Is it easier to stop at point A or point B first? All of these variables combine into a fairly complicated problem that can be solved with computational optimization. Our project served to optimize a road trip to visit national parks in North America. This is mimicking the common traveling salesman problem, where the traveling salesman visits N cities once while distance and cost are minimized. Likewise, this optimization minimizes total distance traveled, thus minimizing travel cost, and also maximizing time spent at the desired national park destinations. This work could easily be extended to support any other vacation planning activities, and potentially support commercial transportation routing as well.
Thanks, Jill. That concludes our presentation. Are there any questions?